The aim of this project is to study how different ARQ protocols perform under different network conditions. In this project, we test stop and wait, go back and selective repeat protocols using a C simulator. We also analyze the effect of parameters such as timeout, window size, and sequence number size under good, moderate, and poor network condition. Finally, we compare the results to determine the best protocol and configuration for our selected network scenarios. For the simulation setup, we use a C-based simulator to test the performance of three ARQ protocols, which are stop and wait, go back and selective repeat. We test several parameters such as timeout, window size, and sequence number size to observe how they affect the protocol performance. The simulation was conducted under three network conditions, which are good, moderate, and poor. Each configuration was tested 100 times to ensure more accurate and reliable results.
In this section, I will explain the performance metric calculation obtained from the ARQ simulation. The raw data generated by the simulator were exported into a CSV file and analyzed using Microsoft Excel. 5 performance metrics were calculated. The first one is throughput, second is good put, and the third one is bandwidth utilization. Next is average delay, and the last one is retransmission ratio. Throughput is calculated by multiplying the total packet sent by the packet size and then dividing the result by the total transmission time. The second one is good put, and good put is calculated by multiplying the total packet target by the packet size and dividing the result by the total transmission time. The third one is bandwidth utilization. Bandwidth utilization is calculated by dividing good put by the available bandwidth and multiplying the result by 100%. And next is average delay. Average delay is calculated by dividing the total transmission time by the total packet target. And the last one is retransmission ratio. Retransmission ratio is calculated by dividing the total packet transmitted by the total packet sent and multiplying the result by 100%. After calculating all metrics in Microsoft Excel, the average values for each metric were obtained. These average results were then used to generate graph and compare the performance of the three ARQ protocol. The first is stop and wait, and second is go back and selective repeat. That's all. Thank you.
My name is Nur Sharafana, and on this part, I will talk about the results, charts, and graph for the calculated metrics graph. And for the first chart is throughput. The chart shows that the throughput achieved by go back and selective repeat and stop and wait under good, moderate and poor network conditions. And for the second chart is good put. This chart shows good put performance of the tested ARQ protocols under different network conditions. And for this part, the first picture is bandwidth utilization. This illustrates the bandwidth utilization achieved by each protocol for the selected deployment scenario. And for the second picture is delay. It compares the average delay experience by packet under different protocols and network conditions. For the last graph, it's retransmission ratio. This shows the retransmission ratio observed for each protocol across the tested network condition.
Latency refers to the time taken for packet and acknowledge to travel through the network. Based on the simulation result, increased latency reduce throughput and good put for all ARQ protocols. This happens because the sender needs to wait longer for acknowledgement before continuing transmission among the protocols. Stop and wait and is the most effective because it can only send one packet at a time before waiting for ACK. Packet loss may occur due to interference, congestion, or transmission error, especially in Wi-Fi 2.4 GHz network. When packet loss increase, throughput and goodput decrease while retransmission ratio and delay increase. The simulation results show that all protocol experience performance degradation under high packet loss condition. However, selective repeat perform better because it retransmit only the lost packet. Timeout, timeout value is the waiting period before retransmission occur. If timeout value is too small, unnecessary retransmission may happen. If the timeout value is too large, package delay increase and throughput decrease. Therefore, an optimal timeout value is important to achieve better efficiency and reliability. Overall,
Window size
the
determine
simulation
how
shows
many
that
packets can be
ARQ protocol
transmitted before
performance is
receiving.
strongly influenced
Acknowledgement.
by
Small
latency
window
packet
size
loss,
limit
time
throughput
out
and
value,
bandwidth
and window size.
utilization.
The Wi-Fi
Less window
2.4
size
improves
GHZ
throughput and
network
efficiency contribute more
because
packet loss,
more
while
packet
the
can be
mobile
sent continuously.
5G backhaul
However,
provide low
excessively
latency and high
large
bandwidth.
window size may
Protocol with
increase
more
retransmission,
efficient
especially for
retransmission
go back and
mechan-
under packet loss
mechanisms
condition.
achieve better overall performance
Window
under
size
unstable
determine
network
how many
condition.
packet can be transmitted before receiving. Acknowledge. Stop and wait is simple to implement but has the lowest throughput and highest delay. Go back and provide better throughput and bandwidth utilization compared to stop and wait. Selective repeat achieve the highest goodput and the lowest retransmission ratio because only lost packets are retransmitted. However, selective repeat requires more complex buffering and packet management. Under good network condition, all protocol perform well because packet loss is minimal. Under moderate condition, selective repeat achieve better throughput and efficient. Under poor condition, selective repeat still maintain better performance because it re- retransmit only lost packet. Meanwhile, go back and retransmit multiple packet and unnecessarily after packet loss occur. Although selective repeat in theoretically more efficient, go back N was selected because the simulation results showed that GBN achieved more stable throughput under the test condition. In addition, the packet loss and latency level were not served enough to significantly reduce GBN performance. Therefore, GBN provide a better balance between throughput, performance, and implementation simplicity. Overall, the simulation shows that ARQ protocol performance is strongly influenced by latency, packet loss, time out value, and window size. The Wi-Fi 2.4 GSZ network contribute more packet loss, while the mobile 5G backhaul provide low latency and high bandwidth. Protocol with more efficient retransmission mechan- mechanisms achieve better overall performance under unstable network conditions.
So, based on the simulation results that we got, network performances was significantly influenced by latency, packet loss, timeout value, and window size. As network conditions deteriorate, throughput and goodput generally decrease while delay and retransmission ratio increase. These findings demonstrate the importance of selecting an appropriate ARQ protocol and configuration for a specific network environment. As you can see here, the Wi-Fi for the Wi-Fi 2.4 GHz access network, Go Back N was identified as the most suitable protocol, and it also consistently achieved strong throughput performance and also maintained efficient data transmission across different network conditions. Although selective repeat in theoretically expected to provide better transmission efficiency, the simulation results indicated that GBN delivered overall performance for the selected access network scenario. Now for the mobile 5G backhaul network, stop and wait ARQ demonstrated the best overall performance according to the simulation results. Despite its simple design and lower theoretical efficiency compared to window-based protocols, stop and wait achieve competitive throughput and stable performance under the tested conditions. The simulation results indicate that the characteristics of the simulated environment allowed the protocol to operate effectively with minimal transmission overhead. Therefore, the recommended configuration for this deployment scenario is go back and ARQ for the Wi-Fi 2.4 GHz access network and stop and wait ARQ for the mobile 5G backhaul network, using the parameter settings that produce the highest throughput and overall efficiency during the simulation. But it should be noted that some simulation outcomes differed from theoretical expectation. In theory, selective repeat is often considered the most efficient ARQ protocol because it retransmits only lost packets. However, the experimental results obtained in this study suggest that go back and stop and wait perform better in the selected scenario. These differences may be attributed to simulator limitations, parameter settings, or specific network conditions used during testing. Nevertheless, the conclusions presented in this report are based on the actual simulation data collected and analyzed throughout the study.